Okay, so do you have any question about the CNN? Okay, if you don't have the question, let me continue about another neural network. Okay, so that one is also very popular one. Okay, that is a recurrent neural network. Okay, it's used in the many applications. Okay, especially when you type something in the Google. Okay, it gives you the many like the suggestion. Okay, and those are like based on that recursive neural network, sorry, recurrent neural network. Okay, this is a class of the deep neural network that allow the previous output to be used as the input to why having the hidden state. Okay, so we can consider like for the normal or standard neural network like this. Okay, we have the output. Okay, we have the hidden node. Okay, we have the input. So this is input, and then we may have more than one hidden node. Okay, and then we transfer the input to the hidden node A, and then from the hidden node we just transfer the output to the output node Y. Okay, like this. Okay, or this is a Y cap it mean like this. Okay, we can read like this. And then, so for this case, okay, whenever we transfer the input, we get the output. Okay, and that is a normal neural network. Okay, we have the hidden states. Okay, but in the recurrence, okay, how they do it, after we send one input at the time t, okay, we record or we feedback, okay, this hidden state, okay, to use as another input in the next die t plus 1, like this. Okay, that we call as a recursive neural network. Okay, in the normal neural network, there's no relationship between the current output and the previous output or previous hidden state or previous input. But in the recurrence, it's not like that. Okay, there's a some relationship between the current output and the previous hidden state or previous input or previous output. Okay, and normally in the recurrent neural network, okay, if the state machines is use a memory of the state to take the information or to record the information from the previous input for the current output. Okay, previous input, or we can say the previous output. Okay, because that output is calculated based on the previous input, like this. Okay, so this is just for the constructed from the neural network to the recurrent neural network. Okay, but as I mentioned that, okay, this is, let's say, D, okay, and this is the output from the D minus 1. Okay, and then we can enroll or we can enfold this one to this one like this. Okay, this is enfolding, this is x0. Sorry, this is D is equal to 0. This is D is equal to 1. This is D is equal to 2. And this is D is equal to D. And for the D is equal to 0, okay, there's no previous output. So there's no input in here. Just tell current input as a D is equal to 0. Okay, but when we consider about the output for D is equal to 1, okay, H1, we consider two inputs. One is that current input H1, and another one is the previous output, or the one from the hidden states. Okay, that is a H0. And based on these two, okay, the current output will be considered, okay, like this. Actually, we have to multiply with weight, okay, and H1 and H0 like this. And then here also, okay, for the H2, the function of W, and for this case, the current input is H2 and H1 from the previous output like this. Okay, normally this one, okay, used for the sequential data. Okay, or another name is a time series data as a language translations. Okay, and also natural language processing, NLP, speech recognition, image captioning, and stock predicting, and many type series prediction. We can use that recursive neural recurrent neural network. Okay, let's consider some example. Like this one is like used in the many LLP. We want to predict what in here. Okay, so predict this one. Okay, what we need is we need the information from the previous what are they, and then based on that, okay, based on this informations, okay, from that we can find the important informations, and then we can predict what should be this what. Okay, in this case, like we can consider as a human. Okay, we can read any word before that one. Okay, so this one's talk about speak difference. So that is mean this word must be like something related to the language. Okay, and then if we read more, okay, so that person grew up in the French. So that is mean this one is mean the language French, like this. And also for this prediction, okay, if we predict this word, okay, we cannot predict on the current information. We have to consider the previous one. And then based on these informations, okay, we can predict this one is maybe it's sunny, the weather is fine, so maybe happy or enjoy or something like that. Okay, we can predict that value. Okay, so in that type of the predictions, okay, you cannot use just the neural network, normal standard neural network, because for the standard neural network, we just rely on the current input. So in this case, the current input is blank, or maybe the one before. Okay, we have to also consider many bars of the previous information. Okay, so in that case, we have to consider the RNN, recurrent neural network, because the recurrent neural network can consider the previous input. Okay, like this, to predict the current value. Okay, in this case also, you need to study. So what should be here? Okay, based on the position, you can consider as the FF, okay, because the last one, or maybe no, something like that. Okay, based on the previous information, machine learning course is very difficult, so you need to study hard or study more, something like that. We can predict some possible value like this. Okay, so normally that's why for RLM is used in the Siri, voice search, or Google Translation, or autocomplete application. Okay, there are many applications used by using the RLM. So in the RLM, like I show you in the previous slides, okay, for each time, okay, or as each time step, okay, the output Y is not only based on the current inputs base, also it's depend on the previous output. In this case, A is mean the output from the previous hitting state. Okay, or yeah, the output of the previous hidden states. Okay, so let's define that one is mean activation function from the previous hidden states. Okay, so this one is current key from the hidden state. Okay, and this YD is mean just a output. Okay, and this is mean the output of the activation function, okay, from here. And then for this hidden state outputs, okay, can be calculated based on the two input. One is A t minus 1, this one, the previous hidden output plus current input. Okay, of course, this is a neural network. You have to multiply with weight. Okay, because those weights will be represent the characteristic or the behavior of your model. Okay, so you have to multiply with the weight. Okay, the weight multiply to the previous output of the activation function, we just define as a WAA. Okay, and this one multiply to the input, we define as a WAA. It depends on the paper. Okay, some people they use a different substrate. Okay, and this one is just a bias. Okay, just a bias. Okay, but we combine the two bias together. Okay, like this, and then it will pass through the activation function. Okay, so if you look in this figure, so the output from the previous hidden state will be used as an input, multiplied with the weight WAA, okay, plus current input multiplied with WAAs, okay, and plus bias, and then it will be passed through to the, this one is a, okay, actually, let's say this one, okay, this is a activation function, okay, and it will generate the current output of the hidden states, AT. And based on this one, okay, we can calculate the output. It will be multiplied for this hidden state outputs will be multiplied with another weight. Okay, so this part is like in the normal neural network. Okay, we have hidden states. We multiply weight in here. This is our input. Okay, so this is mean H. Okay, and then this output, okay, will be passed through to the activation functions. Okay, so this is A, this is G, let's call that H, okay, plus B. If we have bias in here, we got A, and then after that we will pass through to the output O, okay, and this one is equal to, or let's say here Y is equal to, in the O, we have another activation functions. Let's say that is O. Okay. And we have another weight in here. Okay, sorry. We have another weight in here. Okay. So that, let's say WO, we need to multiply with A like this. Okay. So actually, these two equations are the same as in the neural network. The difference is in the neural network, this A, the output of the hidden state or hidden layer is calculated based on the inputs only. Okay, but in the RLL, it's not like this. Okay, this one will be feedback. Okay, so it means it will be summation of the output of the hidden layer from the previous time plus current input. Okay, plus bias, we will get this output. Okay, like this, and then after that is what pass through to there. This one is for the output layer. Okay, like this. So everything the same. only the difference is when we calculate the hidden layer output, okay, we multiply, we also consider the output of the previous hidden layer like this. So that we call as a recurrent neural network. Okay. So in this case, this G1 and G2 are activation functions. Okay. In previously we got as this one is the activation function as a hidden layer. This one we call as a activation function at the, so this is a activation function in the hidden layer, and this is from the output layer. Okay, so this is like this. Okay, and then normally in the recurrent neural network, okay, for here we have just only one layer actually, just one layer, one hidden layer. Okay, as I can say like this. Okay, but the output we feedback to the next layer like this. Okay, that is mean the weight is shared in the all nodes in here, and this is a output layer. Okay, so that is mean all of this time. Okay, we share the only one weight. Okay, and then we updated that one. Okay, one by one like this. Okay, so that's why in the recurrent neural network, okay, it's possible to process any net. Okay, but for this one, okay, start from the line. If you have 100, okay, you can start from the 0 to 100. Okay, you can calculate the output for one time and then update the weight, and then next time update the weight, something like that. Okay, you can calculate for the input for any net, and more and side will not be increased. That will be only the 3 layer. Okay, but this one is depend on your time. Okay, and computation takes account to the historical informations. Okay, and weight are shared across the time. We will use the same weight. We update it for here like this. And after we update it, okay, we use just only one weight. Okay, like this. But computation is quite slow and difficult to access the information from the long time, and cannot consider any further input for the current state. Okay, so normally for the RNN, okay, it's used subway function, and then it's more is used a hyperbolic tangent function, this one. Okay, but sometimes it's also used a subway function. Okay, but the difference is like, please remember that for the subway function, the output is between 0 to 1. Okay, for the hyperbolic tangent function, the output is -1 to 1. And also some cases, we use a preroot functions. Okay, that one is there's no negatives, but for the positive is the same as a input. Okay. How about the backpropagations? Okay, if you look at here, okay, we have the output for every type step. Okay, so this is d is equal to 1, d is equal to 2, d is equal to t, and t is equal to t plus 1, and then t is equal to maybe 100 or 1000, like this. Okay, and then we can calculate the output from each type step, and then we can calculate the error. Okay, this is output from the model and our target, like this. Okay, say like this. And then based on that error, let's say we calculate for 1000 times. Okay, and we have 1000, or It depends on that target value. Okay. And we can find the difference. Okay. We can find the error. Okay. And it's based on the cost functions. Okay. Or loss function. The error is mean actually partial derivative of that loss function with respect to. So in this case, we have to calculate with the A. Okay, so it'll be easy. Instead of 1000, okay, let me consider the error in here. Okay, let's say error in here. Okay, 1 T. This is the output of this time stamp, and then this is our target. Okay, this is our desire. We calculate the error. Okay, so firstly, we have to find partial derivative of that E, or let's say that L. Actually, this is partial derivative of L by partial Y. Okay, with respect to the Y T. Okay, and this Y T is this one. Okay, a function of A. So this Y T can be differentiate with respect to A T. Okay, and this AT, okay, this is here. Okay, this AT is mean a function of A T minus 1 plus or n xt. Okay, so let me write down this one in here. So firstly, this is mean this error. Okay, and that output, okay, partial derivative with respect to AT, and this AT is a function of A T minus 1. Okay, like this, because this is a function of AT minus 1. Okay, and let's forget about this one. Let's find the partial derivative of this one, because this one is output like similar to the convolution. Okay, that error will be transferred to here. So that's why we have to calculate like this. And also this partial derivative of A T minus 1 is a function of, okay, G1 AA will be T minus 2 plus W AS AS T minus 1 plus PA. So that is mean for this AT minus 1 is a function of AT minus 2. Okay, so it just means this one is AT minus 2. And that AT minus 2 is a partial derivative of AT minus 3. And then you have to do that chain rule. Okay, apply the chain rule to find the partial derivative of each functions. And then finally, it's here like this. Okay, so that is mean you have to transfer this error, okay, to the many other type or many other nodes like this, and then our partial derivative is quite long. Okay, so if we use this backpropagation in the real application, okay, we may have one problem. Okay, that is we call as a finishing or exporting the gradients. Okay, because we need to transfer these gradients this error, okay, to the other layer. Not other layer, let's say we can say the other timestamp like this. Okay, and at the end in here, okay, this one can be too small, okay, can be too small, okay, that we call as a vanishing. Or sometimes one of these partial derivatives, these gradients will be too large, okay, getting larger and larger and larger. If you multiply them, okay, this will be over what is called the over the limitation of your computer computation, and then it will appear as a nav, not the number anymore. Okay, that we call as a exploding the gradients. Okay, this problem can be happen in the RNN. Okay, because multiplicated of the gradients can be exponentially increase or decrease. Okay, like in here, you have to multiply many gradients. Okay, with respect to the number of the layer. Okay, in here, please be careful that layer is mean time step of time. Okay, and during the each iteration, the training of each of the neural network will receive update proportional to that partial derivative. If that one is too small, there's no more weight update, or it's too large, your weight will be over limit. Okay, so that is one of the problem in the RNN. Okay, gradient will be vanished into small effectively prevent away from the changing that value. Okay, in the worst case, that may be completely stopped to update your neural network or to learn the neural network from the new data anymore. Okay, or it can be getting larger and larger, and that is well to the export problem. So to control that vanishing and exporting the gradients, okay, in the RNN, okay, what we can modify is we can apply the gates. Okay, the gates. It is being like in the ILL, we transfer the data, okay, from one timestamp to the next timestamp like this. Okay, and we don't pass through all of them. Okay, we control with the gate. Okay, we control with the gate. Okay, but not only one gate, we control it. Okay, we use various type of the gate. Okay, and we modify. Okay, that RNN. Okay, so normally for the RNN, it's used this type of the gate. Okay, the first one is the update gate. Okay, update gate is mean how much past information should model the current output. Okay, normally it's used in the two variation of the RNN. One is a gate recursive unit and is a recurrence unit and LSTM. Okay, I will discuss about LSTM later. And another one is referent gate. Okay, it just means whether the previous information is useful to the current output or not. Okay, drop the previous information. It's also used in that two variations, and that one is a forget gate. Okay, whether the previous information should be forget or erase or pass through. Okay, but that case only used in the LSTM. And fourth one is a output gate. Okay, so how much the cell should be contribute in the output. Okay, that gate used in the okay, in here I will discuss about the ISDL more detail. Okay, for this one you can study by yourself. Okay, so GRU is mean gated recurrent units. GRU. Okay, and LSTM is mean long short-term memory units. This is being it's used in memory, but that memory consider whether should be remember the long information, long of the a very long time information or just short time information. Okay, so it can solve the vanishing gradient problem encountered in the standard RNN. Okay, because in the that gated case, okay, we can adopt that long chains. Okay, so this is mean that small error or small error can doesn't need to be propagated. Okay, something like that. So let me emphasize about that LSTM. Okay, long short term memory. Okay, actually it's invented by this two researcher in the 1997s. But it's not that popular at that time, but currently it's very popular, okay, used in the many applications, okay. And for that one, it's capable of the long time dependence, okay. It just means it can also consider very long term information in your sequence, okay. And also it prevents error vanishing and exploding that fall in the RNN, okay. And in the ISDL, not only the hidden states, okay, there are also one more state that we call as a internal cell state, okay. So which conceptually describe the information that were chosen to retain from the previous units. So this is mean in this ISDL, okay, in the previous one we have the information from the previous hidden states, okay, and then we pass to the current timestamp or current layer. But in this LSTM, we have another pass, okay, later I will show you that one, okay, and then that one also similar to the memory, okay, that we call it an internal cell states C, okay, and the output of this next C, okay, will be depend on both of them, okay, and application speed recognitions, yeah, handwriting text to speech, and then many applications, okay. So this is the structure of one unit, okay, one unit in the LSTL, okay, one unit at a time D, okay. If you consider okay, if you consider your sequence with the 5, okay, let's say this is 5, 4, 3, 2, 1. You need to have 5 units like this, okay. And then if you consider 10 input each die, okay, you have to consider time 10 unit of like this, okay. So this unit or this cell we call it a LSTM unit or cell, okay. It's similar to the IL, okay. For this one, it's for the die key, okay. If you have 5 input, okay, this is D minus 1 from the line that you need to have the 5 like this, okay. Inside each cell, okay, like I mentioned that it's used a various type of the gates, okay, especially these 3 gates, okay. In sandpaper, it's like the 4 gate, okay. There are another gate also, but in here I will follow that 3 gates, okay. The first one is a forget gate, okay. That determines the information to forget that are not imported from the bus data, especially this is from the C, okay, the previous cell state, okay. And then whether we should remember or not, okay, is controlled by this gates, okay. Actually it's here, this one F, okay. And another gate is we call it a input gate. Okay, so the gate in here is being, if you have studied about the control system, okay, just a multiplication. Okay, so this is your control. Okay, this is your input. Okay, let's say if your control is 0, there's no output. Okay, if your control is 1, the output is your input A, like this. Okay, so this is mean that gate, okay, that control, and this is gate control. Okay, so this forget gate control this C D minus 1. Okay, so C D minus 1 is the information from the previous cell state. Okay, this one is from the previous hidden state. Okay, so this set state is controlled by this hidden state from the previous cell or previous unit plus the current. This is mean the current input. Okay, and then this sigma, okay, all for this sigma are sigmoid function. Okay, sigmoid function. So that is when forget gate is control the input from the set states based on the input from the hidden state and input. Okay, and this input gate is determined. The information is imported to pass the current internal cell states. Okay, so actually we have this two. Okay, we pass through to this C. Okay, by using this SAM, and that one, okay, must be passed to the hypotenuse functions. Okay, but whether it should be passed to here or not is controlled by this input. Okay, so that is mean this input gate will be controlled, okay, whether these two information, the current input and the information from the hidden state should be passed through to this our memory or the cell states or not. Or we need to edit that information to here or not. Okay, like this. And the last gate is the output gates. Okay, so if you look at all of the gates, okay, those gates control is output of the subway functions. Okay, and input is also the same. Okay, all of that three. Okay, use input as a that hitting the state from the previous one and then input. Okay, so that's what, let me write out like this. For all the gates, okay, all of the gates are subway functions, okay, but with the input of this one and this one. Okay, this is mean previous hidden state, and this is a current input. The previous. Okay, like this, but of course you have to multiply with weight for all of that. Okay, different weight. Okay, so that's why the gate is controlled by them, that 2 multiplied with weight. Okay, but this one is control what? Okay, we have the seed. Okay, this has been current cell states output and pass through to there. Okay, this arrow is here, but to the another hypothetical hyperbolic tangents. Okay, that output will be contribute to the next hidden states. Actually, this is as well as a output. Okay, so output. Actually, this one is the same as the output from previous, or maybe short, previous output. Okay, previous output. Okay, and that output, okay, is depend on this cell state, the current cell state. This one is mean the current cell state. Okay, but how much it should be contribute, okay, is controlled by this Fourier function, this gate, the output gate. Okay, so all of the gates use the output from the previous extent and current input as a control. Okay, like this. So the difference between the standard RNN and LSTM. Okay, in the previous case, we pass all the information from the previous output plus in current input to the next. Okay, in here also we pass all previous output and input to the next output like this. But this is mean the standard I. And this is ILDM. It's not like that. Okay, so for this C, okay, whether D minus 1 and this is CD should be contribute to the current time CD or not. It depends on the current input and also previous output. We control it. Okay. And that two value, okay, previous output plus current input. Okay, how much of them have to be added to this CD is controlled by themselves also. Okay, by using this Sigmoid functions. And how much this CD should be included in the HD in the output, the same as YD, is also controlled by that too. Okay, so in here we use the two activation functions. Okay, the first one is a Sigmoid function. Okay, so that Sigmoid function output is 1 or 0. 1 is mean, okay, it's passed through all of them. 0 is mean get out totally. Okay, like this. But for the hyperbolic tangent function, okay, it's between 1 and minus 1. Okay, within that range. Okay, so that is mean either case, okay, have same value, but for the Sigmoid functions, okay, 1 and 0. Not 1 and between 1 and 0. 1 is mean it can pass the whole, maybe between that 1, maybe some part, or 0 is mean to get out. Okay, this is not like that. Okay, so let's look at the characteristic of each of then in the LSTL. Okay, the first one is, as I mentioned, that not only transfer the output or hidden state output, it's also transfer another information that we call as a cell. Okay, so this should be the state. Okay, actually it's a long-term information. Okay, to carry the information from the past. This is like this. Okay, this one is not appear in the IL. Okay, only in the this LSTM. Okay, so if we have another timestamp, okay, we have that one here, and then it will pass to the another timestamp. Okay, that one is controlled by gate in here, so this is mean the gate. Okay, so this gate will be passed through the Sigmoid functions. Okay, let's see. Okay, yeah, like this. Okay, so this is one characteristic in the LSTM. So let's consider one by one. Let's consider gate one by one. Okay, the first one is a forget gate. Okay, that forget gate control this C D minus 1 from the previous state. Okay, this is a simul function. Okay, that simul function use the two inputs. Okay, this one is okay. I can say that output or hidden state from previous time step. Okay, this one, and this is a current input. Okay, both of them have to multiply with respective weight. Okay, of course, that weight is very important in the neural network. Okay, so in this case, we can say that this is the functions. Okay, W. This one is less the X. H multiplied with this one. Okay, all for them are factor plus WF H D, okay, plus PF like this. Okay, so it's depend on that. This is the previous output. This is current input multiplied with respective weights plus bias and pass to the signal function. Okay, so this output is mostly 0 or 1, but between, okay, this is like this, between 0 and 1. 0 is mean close the gate. Okay, 1 is mean fully open the gate. Okay, and then very small amount is within this range, like this. Another gate is a input gate or dense layer, or sometimes we call it a modulation layer. Okay, for the inputs, okay, it's similar to the previous equation. Only the difference is this weight. Okay, in this case, we use a weight F, weight for forget gates. This one is weight for input gates. Multiply with the hidden state from the previous one and input plus another bias pass to the signal function. So this one will be similar to the previous one. Okay, 0 to 1. Okay, so this is 0, this is 1. Okay, so it's this mean it's control this one. And what is this one? Okay, it's control this flow. Okay, in this flow, this is maybe temporarily cell states. Okay, but this one is not the real or the current cell state yet. Okay, let's say this is just for the temporary. Okay, or we call it the output of the depth layer. Okay, so that calculation, this one and this one is the same. Okay, the difference is different weight. And instead of the signal function, we use the hyperbolic tangent functions. Okay, so this is mean the information for the cell states, current cell states. Okay, or information, maybe I can say that current information flow. Okay, the current is being based on the current inputs and the previous outputs. Okay, whether it should be passed to the previous C or not is controlled by this input gate. Okay, And this one, if 0 is mean no current information will be passed through to current C. If 1 is mean fully contribute like this. Okay. And this is mean the currents of the new cell state, okay, that will be passed to the next. This will be calculated by using, okay, this one multiplied with this one, okay. So this is gate of the forget, output of the forget gate, multiplied with the previous cell state, plus this is from the current information. Okay, it's controlled by input gates. And then we edit that too, and then we calculate this current cell state. Okay, it's included information from the previous, okay, depend on the this gate, and also it's included information from the current input. Okay, and then based on this CT, the output will be calculated. Okay, so that output is not, okay, sorry, I forgot the gate in here. It's not passed through to the output. That C will not pass through to the outputs. This will be controlled by another gate, output gate. Okay, and then that output gate is also used the same input as a other two gates. Okay, HD and then ACE. This is input and previous output multiplied with another weight. Okay, plus bias pass through the subwave functions. So that one also 0 to 1. 0 is mean this output doesn't include this C D anymore. 1 is mean fully. Okay, so like this. And then the output, actually this is the output or output of the hidden state here the same. Okay, output at time T, or the output of the hidden state at time T, because it will transfer to the next. Okay, it will be calculated. So this is a gate, can be 0, between 0 and 1, and then the real output is calculated based on this cell state. Pass through the addition function, we use the tanh function. Okay, this one. Okay, and if 0, okay, so this output will be 0. If 1, okay, this is mean only this one, but it will be, can be also between 0 and 1 like this. Okay, so in this case, if we summarize, okay, in the LSTL, okay, how many weight we have to calculate? Okay, the first one is from the forget gate. Okay, we have to calculate weight for the previous plus this one. Okay, so here we have for the forget gate and bias for the forget gates. And then after that, we have to calculate weight for the input and weight for bias for the input. Okay, this is one pair. And then weight for the output, bias for the output. Okay, so this is for the forget, and this is for the input, and this is for the output. Okay, so we have to update many weight like this. Okay, and if we go back to this one, okay, for the RNN, we need to update only two weights. Okay, we can say that the weight at the hidden node and weight at the output node. Okay, but in the LSTL, okay, we have to update many weight like this. Okay, and sorry, I forgot this WC also. Wait for the new cell. BC. Okay, this is for this one. Okay, and there's no weight in here. Okay, so that's why you have to calculate the full weight. Okay, so it seems to be more complex, but this gate will control whether this bus information should be passed through to the next time or not. Okay, so that's why it can eliminate. Okay, eliminate these problems. Okay, exploding or vanishing gradients. Okay, because sometimes you have to recalculate new gradient, something like that. Okay, so this is about the LSTL. Okay, so do you have any questions? So before I start, let me discuss about the project. Okay.